Oh, we're just about there. Welcome back, everyone. Oh, didn't want to do that. There we go. Well, it's official. We're now in week number 9. Welcome back, folks. So the big news is that we got through the midterm. Well, not exactly a midterm. It was an ordinary 50-minute exam, but your course score on that exam is going to be your midterm score. If you'd like to take a look in the feedback or see the solutions, they're posted here. I directly emailed back everyone your graded exam to. So if you haven't seen it yet, check your ISU email address. If you still don't see it, let me know as soon as possible and I get it sent right over to you. Either send me a message through the Canvas system here or just send me a direct email message and I'll get your exam sent right back to you. Well, we left off a week ago today, working through section 7.1. We're pretty much just about done with it. We have 2 more key examples we want to look at, a little document on avoiding circular logic, and then we'll move into section 7.2, the sum and difference identities. But any questions at the moment, folks, at all to get us started? Okay, well, let's dive in. We're in section 7.1, example 4. Well, let me get that annotation off of there. But this is the last example that we took a look at before going on the weekend last Wednesday. I think I might have said Thursday on accident. We're verifying that identities are true trigonometric identities, that this formula will hold for all values of theta in the domain on the left-hand side and the right-hand side simultaneously. And sometimes these can be pretty tricky problems. So we have 3 different strategies to really work through. We used strategy number 2, where we took the right-hand side. It looked like a good side to just start simplifying, took a bunch of algebraic steps. In yellow, we used a trigonometric identity. And we ended up on the left-hand side. We obeyed ordinary rules of algebra. And so going from here, the very top, all the way to the left, proves that this is a true equation. It's an identity once and for all. It's kind of a strange process when you look at it. Ordinarily, if you see an equation like this, you might think to yourself, we're solving for a variable theta, but that's not the case. We're trying to show that this holds for all theta in the domain of both sides. Any questions at all with the run through on this one? Okay, so as far as the strategy goes, these methods are pretty much saying start on one side of the equation or the other, simplify it like we did on the problems above on this document until one side looks just exactly like the other side. You don't have to copy the whole equation down as you go. You can just focus on one side, simplify it down, and try to get to the other. But sometimes that's pretty tough to do, like we mentioned before. So on the next problem, we're going to try out strategy 3. If we can't connect both sides, then just work on both sides independently and try to get it down to some common thing. This moment the same algebraic expression emerges on both sides, you've proven that both sides are equal and the identity is proven. That's kind of what goes down on this one. I think if you're really clever with this, maybe if you have a moment of inspiration or you just work with it long enough, you can start on one side, end up on the other. But this is a good one to kind of split it up into 2 parts. So we'll try it off on this one. So what I can't do on this is multiply both sides of the equation by one value or another. I can't clear denominators because the moment you work on both sides of the equation, you're assuming that that equality is real. But it's our job to verify that the equality actually holds. We can't show it holds by assuming it holds. That's the idea of avoiding circular logic. And so that's the mention that you see here in the instructions as well. If you did multiply something through on both sides of the equation, your proof is not correct, but on my grading your homework, I'd mention that, and I'll give you an opportunity to rewrite it to reclaim the points. Mainly, we're just getting ready for this, so when it comes back on the 3rd exam, we know about how it should go, how they would be graded. So starting this off, I'm going to work on the left-hand side, do something to it, try to simplify it down. First thing I can see is you can rewrite secant as 1 over cosine. So left-hand side is cosine phi, 1 plus 1 over cosine phi. Next thing you can try is clear the denominator on this expression we see. And the denominator can be cleared by just multiplying by the number 1. Number one written in the form of cosine phi over cosine phi. The idea now is we can multiply across the numerators and get cosine squared phi. When we multiply across the denominators, we do get our cancellation. And so the multiplication will go like this. Multiply here to here for cosine phi. Plus, multiply here to here causes a cancellation. That's cosine phi over cosine phi. So now it's just plus 1. So we have cosine squared phi divided by cosine phi plus 1. And this is what we're aiming for. 1 minus cosine phi divided by tangent squared phi. Somehow we have to transform that denominator into a tangent squared, and the numerator cosine squared needs to turn into 1 minus cosine phi. There's got to be a way to do that, but again, this example is pretty tricky. If you're not sure what to do on the next step, there's not a bad idea to just break it down into look at the right-hand side instead, see what we can do from there. Maybe if we work on the right-hand side and we're clever enough and we have the right inspiration, think of the right identity, we can get all the way to the left-hand side. But if we don't quite make it there, if we can at least get there, the proof is done, because then we can just work backwards and connect it right back to the left-hand side. And just a reminder on the notation that we're using here, left-hand side literally just means left side of the equation, LHS. And right-hand side just really means this side, RHS. So now let's start with the right-hand side of the equation. We can simplify it by either using a trigonometric identity or just, let's go with the same approach. Rewrite tangent squared in terms of sines and cosines. This then turns into 1 minus cosine phi. Denominator is sine squared phi. Divide by cosine squared phi. And if you've proven this one already, maybe you're just bored and you gave this a look, you might find my approach to this kind of weird. But that's the fun thing about these kind of verifications that we're doing. A lot of people can have a different take on this, a different way to go at it, and your idea might be just as correct as this one. So I'm going to go with the same approach from before. Let's clear denominators. Well, that's just going to be multiplying by the reciprocal of that denominator. This is going to turn into 1 minus cosine phi multiplied by, take the reciprocal of that denominator, cosine squared phi. Let me try a little bit harder on that penmanship. Cosine squared phi divided by sine squared phi. Now it's starting to look really kind of nasty in a certain sense. We're trying to get cosine squared, just cosine squared the numerator. So this is nice just the way it is. We wouldn't want to distribute cosine squared into this group because then we don't get what we want, that part matching up with this part. We have to somehow cancel 1 minus cosine phi into sine squared phi. And you know what? That is actually possible. We can make that cancellation happen. Let me show you one way to try this out. So when you see sine squared, think in terms of the Pythagorean identity, sine squared phi plus cosine squared phi is 1. Solve for sine squared. Sine squared phi is 1 minus cosine squared phi. We'll substitute 1 minus cosine squared into that denominator right there. So this is one of those problems where it gets a little bit worse before it gets better. This is the worst part before it gets better, but we're making progress. 1 minus cosine phi, copying in, times cosine squared phi. Here's the identity. Sine squared is 1 minus cosine squared. Color coding just to show the substitution. We can't cancel in that form, but it does reduce this parenthesis here into this parenthesis, this group right here. The way it reduces is my favorite factoring formula of all time. That's a difference of squares. It has the form a squared minus, you would often say b squared, but let's say c squared, c for cosine. A squared minus c squared will always factor as a plus c. Let's actually change the order. A minus c times a plus c. That's just a slightly convenient order for us. The a squared is just a 1 because 1 can be rewritten as 1 squared. So in other words, 1 squared minus c squared is equal to 1 minus c times 1 plus c. Think of this c as just being a cosine phi. This 1 minus c here is going to cancel with this 1 minus c right here. And keep in mind, again, this is just one way to do this identity. You might have thought of a nicer way that makes more sense to you, and it's equally valid. But continuing in this approach, we have copy the entire numerator, 1 minus cosine phi times cosine squared phi, factorization of that denominator. Let's use purple just to emphasize the connection there. This factors as a 1 minus cosine phi times 1 plus cosine phi. And finally, here's the nice cancellation. That cancels with that, and it leaves behind cosine squared phi divided by 1 plus cosine phi. At this point, you might still work with this. In fact, you can go backwards all the way to the left-hand side, but our work is immediately done right at this stage. Cosine squared phi divided by cosine phi plus 1 is what we wrote the left-hand side as. The right-hand side is also equal to the same exact thing, so we can conclude by saying, therefore, the triangles here, little triangle dot is just a way to say, therefore, the left-hand side is in fact equal to the right-hand side. And so our work is done. This shows it's a bona fide identity. I don't know how useful this one is, but it's a fun one to just show the idea that you can work independently on one side, the other, just match it up, and then your work is done. Well, this one's kind of intense. The next one is not as bad, I think, but we'll try one more just to close out the notes. Any questions at all getting through this one? Okay, and again, if you've worked with this original equation, if you multiplied both sides of this equation by something, there might have been a quicker way to see that it could have been a true identity, but we would have been in the land of circular logic at that point. And so that's what the discussion way back here on this additional document, Avoiding Circular Logic, is all about. Let's pause, just take a mental break on that last problem by taking a look at this other document. So in mathematics, the big maxim that we say often is we have to mean what we say, we have to say what we mean. And this is what avoiding circular logic is all about and how it can present itself, circular logic that is, in this course. So I'll highlight where circular logic appears in proving this identity here. It's just another random identity like the ones we've been doing in the notes. 1 over sine minus sine equals cotangent times cosine theta. And one thought about this is you could start solving this identity by expressing cotangent as cosine divided by sine. We wrote down the whole equation, and that part's not wrong at all. If you write down the whole equation on every step, then you can have a valid proof going in that direction. The problem occurs right on this line. The thought is there's a sign in this denominator, a sign in this denominator, and the equation would look simpler if we were to clear the denominator. So right on this step, this is the circular logic. We multiplied both sides of this equation by sine theta. That means we're assuming that the equality is valid. This one right up here. But if that's what we're meant to show, we can't show it's valid by assuming it's valid. We've gone in a literal circle with the logic there. So right at this step, because we multiply both sides by sine theta, this is circular logic. If it happens in homework, say at about 5-point problem, you could lose 3 points, but I'll give you an opportunity to correct the proof. In fact, there is a good way to correct it. If you continue on looking at how this goes, sine theta multiplies in here, leaving a 1. Sine theta times negative sine theta gives us negative sine squared theta. Denominator clears here, we get cosine squared. That's a familiar identity, right? On this next step, we're adding sine squared to both sides. And we get the Pythagorean identity, 1 equals cosine squared plus sine squared. So it feels like there's something right about this. The only problem was we literally did go in a circle by assuming it's true, but we can fix it. First, just for the sake of a screenshot, I want to highlight this part right here. Let's just drop it in our notes. This is what we mean by avoiding circular logic. We'll have it there for all time in our notes. But the way you correct this proof is actually not too bad. Think of all of this as scratch paper work. You can make this a valid proof by starting right here. This is not circular logic because this is a known identity already proven to be true. We proved the truth of this identity in section 5.2, for example. So if you start with this identity, manipulate it by subtracting sine squared from both sides, dividing sine into both sides, dividing the left-hand side by sine to get 1 over sine, sine squared over sine, and simplify. This was the original identity down here that we were trying to prove, and this logic is valid going in that direction. So if you rewrite the proof, this is what it would look like. And we didn't mention this proof technique at all when we were doing the notes, only because oftentimes it's pretty tricky. If you're trying to show that this is true, it's hard to know, where do I even start? How do I know I'm going to end up here, for example, and work backwards? So knowing that you had to do that meant you'd write out all of these steps, then present it in a logically sound way. You have to now reverse the steps. You have to start from something that's known true. That's like double the work. And that's the reason it's not the most favored proof technique. But if you're doing this as an exam problem or a homework problem, and that's what makes the most sense to you, it is valid and you're not going to lose any points for it. It just took a long time to write out. So this is the correct approach. Another approach is highly recommended. I kind of emphasized here. Start on one side, the cotangent cosine side, simplify it down until it looks like the other side, 1 over sine minus sine, and that's really all you have to do. This is the cleanest proof you can pretty much give to an identity like this one. This one takes some ingenuity, and it took double the work to make it sound. I should close that out. Let's take a moment to think about this one. Does that make sense to folks on the issues with circular logic and how to correct it? Okay, well, returning to our notes, here's just a reminder that it's okay to copy the equations down, but if we do one thing to one side and the other side simultaneously, we assume the equation is true right at that step. So with that in mind, let's try out one more identity. Let me see if I can, probably can't fit it up there. Here's the last one for the notes. We have cotangent divided by cotangent plus tangent. This is a weird looking identity, but somehow this arrangement of cotangents and tangents is just a clever way to write down cosine squared. We'll verify this is true, not by assuming it's true from the start, but let's work from the left-hand side and see what we can get out of that. I usually pick the more complicated side oftentimes because you can reduce something a lot easier often than it is to take something that's pretty simple and make it convoluted and complicated like the opposite side. I don't see how to make cosine squared into this, but surely we can find a way to simplify this. So let's copy down cotangent theta divided by cotangent theta plus tangent theta. The last problem we solved, we did it in kind of a brute force way. We took everything, wrote it in terms of cosines and sines, and that would probably work on this one as well. But let's go for a slightly different approach, just for the sake of variety. One thing that might strike you as interesting is there's a cotangent in the numerator, tangent in the denominator, and it just so happens to turn out that cotangent theta times tangent theta, that's exactly 1. That's just because cotangent is cosine over sine. Tangent theta is the reciprocal function, so anytime you multiply a function by its reciprocal, we expect this cancellation. And we just get a 1 out. So thinking along those terms, let's multiply this by, here's the weird step, cotangent theta divided by cotangent theta. Something weird like this could have worked on the very last problem, but we didn't emphasize it. So that's why the algebra kind of got intense on that last example. Multiply across the numerators, and it's cotangent squared theta. In the denominator, we do have to distribute. So cotangent times cotangent here is another cotangent squared theta. Cotangent times tangent here, that's the plus one. And that's another identity. Recall that there's three Pythagorean identities. We often think in terms of the sine squared plus cosine squared is one. But another one goes tangent squared theta plus one is secant squared theta. There's a third, but there's a great mnemonic for getting the third identity. This one we do have to memorize, or memorize the trick to derive it. You take sine squared plus cosine squared is one. You just divide the whole thing by cosine squared. But the idea with this one is if you change from the function to a cofunction, tangent squared into cotangent squared theta, secant into its cofunction, secant squared into cosecant squared theta, it's the right identity. That's kind of slick in a way that you can go from function to cofunction on both sides and get the right identities either way you do it. So cotangent squared plus one is nothing but a cosecant squared. Let's drop that into the denominator here. Left-hand side is now cotangent squared theta. Divide by cosecant squared theta. And now, I'm not exactly sure what I would do with all this, but at this point, we might start writing things down in terms of sines and cosines and see if we can simplify it with the objective of trying to get a cosine squared out. You could do this in stages. Cotangent squared, let me just leave it right where it is. If you have a function in the denominator like this one, you can bring it up into the numerator and just put in its cofunction. So the identity or the idea with that one is 1 over a cosine, or let me try it a little harder, 1 over a cosecant theta, we have squared version, I'll just do it with power 1, is the same as sine theta. So change the position of this function right here, just go to the reciprocal version, sine theta, it'll be squared. But now this means it simplifies in a huge way because cotangent squared is cosine squared divided by sine squared. So next thing to write is cosine squared theta divided by sine squared theta in place of where the cotangent was, times the sine squared. That's a simplification going this way. That seems kind of abrupt. I feel like it's easier to reread the notes if we cancel like that, just a little bit lighter. It's now a cosine squared theta, which was, well, is the right-hand side. At this point, we have a long connecting chain of equalities, and that's our objective. You can link up one side to the other with equalities. You've proven that this is a true identity. We never started by assuming it's true whatsoever, so we don't have any kind of circular logic whatsoever with this one. Lots of ways to do this. If you wrote this in terms of cosine divided by sine theta, same here, and then sine theta divided by cosine theta, you could start clearing denominators and get the same effect down below here. Probably a different Pythagorean identity would come up. Well, any last questions at all, folks, with this example 5? Okay, that's pretty intense problems. The homework has a few problems like this. Not all of them are as hard as these. Some of them are a little bit nicer, just getting started. If you get stuck on any one of those problems, like I mentioned before, don't hesitate to reach out. Send me an email, drop into office hours. I'll be very happy to help. There's no secrets with solving these. So try what you can. And if you get stuck, I'm happy to help work them out. Next section we're going to look into is more identities. That's pretty much the goal of chapter 7 until we do equation solving at the end. But these are sometimes considered the most fundamental identities after the ones we just looked into, the Pythagorean ones, of trigonometry. Our book calls them the sum and difference identities. A lot of books just simply call this the addition formulas, even though there's ones with subtraction as the difference would suggest. Because that's such a common name to just say the addition formulas, we should say it right up here at the very top of the notes. These are the sum and difference identities, also known as the addition formulas. Our book made some really weird choices on some of the things that they named. Oftentimes I might just accidentally say the additional formulas, but I'll try to say sum and difference identities because that's what's in our actual book. Starts off with some crazy diagrams. Let's ignore that for just a moment. These are the addition formulas or the sum and difference identities. Looks like I actually wrote in the additional formulas here. Let me just also mention this is the addition formulas or the sum and difference identities. So the emphasis is these two ways of naming these will be considered synonymous. But here they are. There's four interesting identities. The reason they're called the sum identities is because of the plus here. There's a way to break down sign with two different inputs. The breakdown is a little bit messy, but sometimes that's to a major benefit. If there's a minus, we put a minus right there. Cosine has the same kind of property. Plus has an interesting interchange, goes to minus, and minus goes to plus. And this is just kind of a new pattern that we're going to work with and memorize. Tangent has its own set of rules. Tangent alpha plus beta looks like this. If it's a minus, it has a slightly different version. And we don't have any formulas here directly for secant, cosecant, cotangent. But the major reason for that is you just take the reciprocal of all of these three, and you have the dual identity for those other functions. We're mainly going to be focusing on the identities as we see them here, however. But if you're like me and you're seeing these for the very first time and you're thinking, when I remember seeing these for the first time, you're thinking, that seems really random that these would be true. That's what the purpose is for the first page of these notes, just to give a quick verification. We're going to show this one is true. There's three others that you would prove, but the reading shows a slick way to derive others. Once you prove just one, you can make a connection with the other ones. So I'll leave the other derivations for the reading. So let's go back up here. This is kind of a rough page to look into when you just open up these notes. So look into it in stages. We're going to do the derivation for this difference identity. Cosine s minus t equals cosine s cosine t plus sine s sine t. The major idea with the derivation is it's all about the distance formula. So this is a nice call out to the distance formula for algebra way back in the day. The difference between 2 points in the plane, x1, y1, x2, y2, is the distance equals square root. Difference in the x-coordinates squared plus the difference in the y-coordinates squared. So we'll use this formula twice. Now I have two interesting diagrams here. Part A diagram, the part B diagram. We're going to apply the distance formula between the points P and Q on both diagrams. But first, let's see why we're doing that. That's just as important, I would say. We're trying to do an identity for cosine s minus t. Involves cosine s cosine t, sine s sine t. And that's the stuff we have right here. Cosine s sine s, cosine t sine t. Cosine s minus t also emerges right here. Where did sine s minus t go? Who knows? We'll have to look into that as we go to solve this thing. So that's the connection with the diagram and the thing we're trying to prove, this first difference identity. And so we have angles s and t. We just dropped an angle s here, angle t here. See the diagram with the arrows measured in standard position. Looks like they're positive angles. They can terminate in any quadrant, but to make the diagram simple, we had it terminating in quadrant 1 and quadrant 2. So we have a definite diagram to look at. The other thing to focus on in this diagram is if this is the angle t, and this is the angle s going all the way, if you shorten it going this much, that would be just the angle s minus t because it's missing this bit of rotation right here. So that inner angle is the angle S minus t going this way. Does that make sense to folks on just the angles in the diagram that we see? Okay, now we hit it with the distance formula. There's two coordinates here, so a good way to think about this is this would be your x1, this would be your y1. Let me fix that x first. This would be your x2, this would be your y2, and applying this, we would take the difference in the x coordinates. So that would be, if you go x2 minus x1, here's x2, cosine s, and here's x1, cosine t. So we applied this formula directly using the x coordinates, and we squared the difference. Do the same thing, you would take a y2 minus y1, so y2 is sine s, that corresponds to the right thing here, minus y1 is sine t, and it corresponds to that same value there as well. Then we just do it all over again in this diagram. We're gonna have to do stuff with this algebraically, but this is just the start of the derivation. We now know the distance from this point to this point. And then something really interesting happens in the very next diagram, the figure B. If you take this whole thing, this whole structure, that goes from here to here to here, and you just rotate it in a rigid way by an angle t in the clockwise direction, you would get this structure. So here it is. The inner angle s minus t is the same because we didn't change the lengths of any of these. We just took the whole thing, rotated clockwise by the angle t, so that this angle, or this side here, is now landing right here, overlapping the x-axis. So angle s minus t is exactly the same. We like the x-axis because it's easy to say exactly what that coordinate is. It's the unit circle, so it has to be coordinate 1, 0. And because the inner angle is s minus t, the angles here are also s minus t as well for both sine and cosine. So that's the next stage of the derivation. We take this weird looking triangle, rotate it back clockwise by the angle t, and this gives us a new set of points, x1, y1, x2, y2. We take the difference in the x coordinates down below, x2. Well, x2 is this thing, cosine s minus t, minus x1. x1 is just the positive one. Do it again for y2. That's sine s minus t minus y1. y1 mercifully is a 0. This is going to help the algebra just a little bit. And that's just now using the distance formula twice. There's a lot of stuff on here, so try not to look at all the diagram all at once. Don't look at the forest, just look at the individual trees and how it connects down to the distance formula. But now here's the major thought. What makes this something that we can work with algebraically is the fact that this segment right here is exactly equal to this segment. It was rigidly rotated. The distance between the points didn't change whatsoever. So the distance is being equal tells us you can take this whole thing and just drop it in, this whole thing and drop it in, set them equal to each other. This is the major idea for the derivation of the distance formula. This is, I think the book mentions, this is a really, really old idea. So this is an idea that's hundreds of years old. And that's kind of fun in a way, looking into old ideas from many, many years ago for deriving this relation. In fact, this relation has been known for thousands of years. That's the weird thing about this fact. But this is just a clever proof. After Cartesian coordinate systems were put down, people found a quick way to derive it. So now we're on this identity. But that's an equation we can work with. We're not doing anything circular here whatsoever because we're using a known fact. The distances are equal. So anything you do algebraically with a known equality here is fair game. We can square both sides. If we do that, the square roots fall off. Let's do just that. Square both sides and you get cosine s minus cosine t squared, which means we have to FOIL cosine s minus cosine t. Cosine s minus cosine t. You know what? I'm not going to be able to fit that horizontally. I'm just going to write it squared like this. I'll carefully work it out algebraically. Plus sine s minus sine t squared is now equal to this whole thing without the square root, cosine s minus t minus 1 squared plus, this one simplifies. This is just sine s minus t squared. The minus 0 has no effect. So this is the one slight simplification so far. So this is the next identity that we can work with. We can now expand out these two things here, here, and the third one over here, and start simplifying. So it's pretty much just all algebra from here down. My hope is that we can fit this in this one page. So expand this out. We'll have cosine squared s. We also multiply here to here when we FOIL, so that's cosine s times cosine t. But we get two copies because FOILing would give a second multiplication. So plus 2 cosine s cosine t. Then last, you would get cosine squared t. Then we do it all over again here for the sines. It'll be sine times sine, sine squared s. It'll be sine s times sine t, but twice. So this is going to be, hang on, let me double check my signs. When I multiplied here to here, that would have been a negative cosine s cosine t. So that should have been a negative sign there. Sorry for that error and distraction. Same idea on this one. FOILing this out is going to give us a negative sine s sine t, then two copies. So minus 2 sine s sine t. Last, it's going to be sine t times itself, so plus sine squared t. And that's the entire left-hand side. My hope is to get this all in one line, but we'll see how close we get. We'll FOIL out this one. It's going to be cosine s minus t squared to start. Cosine squared s minus t. Then it multiplies the negative 1 for a negative cosine s minus t, but we get two copies of that. Minus 2 cosine s minus t. Then it'll be negative 1 times negative 1 plus 1 squared, or just plus 1, plus sine squared s minus t. So now it's a gigantic mess. But keep in mind, there's a big simplification here because we know cosine squared of an angle theta plus sine squared of the same angle theta is 1. And there's lots of stuff like that we're looking at. Cosine squared s plus sine squared s, that's 1 already. And cosine squared t, sine squared t, that's 1 already as well. Everything in yellow combines for the number 2. We just have two copies of this idea. So the left-hand side, following the yellow highlighting of the identity, gives us 2 through that identity. And then a bunch of mess. We can't do anything with this stuff. Minus 2 cosine s cosine t minus 2 sine s sine t equals, we also have another nice thing we can do here. The angle s minus t is repeated. So that takes the role of theta over here. This is just a 1 plus that 1, giving us a 2 again. Let me highlight that in yellow, and the 1 as well, since we combined it. Minus 2 cosine s minus t. Next miracle that happens algebraically is you could just subtract 2 from both sides. Those just cancel off immediately. Next thing you can do is just divide both sides by negative 2. It's a factor in every single term that survived. If we divide all sides by negative 2, we get cosine s cosine t plus sine s sine t equals cosine s minus t. In fact, that's exactly what we want to show. It's this one, written in a different order. Alpha is playing the role of s, beta is playing the role of t, cosine s minus t becomes cosine s cosine t. Here we have cosine alpha cosine beta plus sine alpha, sine beta. That'd be the sine S, sine T. Variables are different, but the identity is the same algebraically. So it's kind of a wild adventure. It's kind of neat to see ideas with angles in trigonometry connecting with the distance formula out of nowhere. And then it just became a interesting trigonometric identity that we proved, getting all the way down to this line. The trouble is that there's four of them, and then two more if you include tangent. But any questions at the moment, seeing that derivation? Yeah.
How did you get the two on the right-hand side?
Oh, this right here, the cosine squared s minus t, and this sine squared.
Lost there.
Yeah, these two combined to a one.
That makes sense.
And then it was just plus this one right here to balance out to two. So I combined all three of these things here in yellow to get the two together.
My brain was associating that other sine squared t is on the left side.
Oh, I gotcha. Yeah. Other questions at the moment? Okay. Well, now that we're past the derivation, let's leave it here in case there's follow-up questions. Here's another fun thought about these identities. There's a humongous pattern here when you really look at it closely. First thing you want to think about is what happens with the signs. If you're looking at the sine version, plus in the middle corresponds to plus in the middle, negative in the middle corresponds to negative in the middle, and then it flips for the cosine version. Plus goes to minus, and minus goes to plus. That's one to watch out for. Other thing to keep in mind is there is a pattern for sine. The sine version goes sine, cosine, cosine, sine on both versions. There's a new pattern for cosine. The cosine versions go cosine, cosine, then sine, sine, both versions. The last thing that's really nice about this is the way these angles are arranged. This is the best way to write all these formulas because it's a striking pattern. Alpha always comes first. Beta always comes last on every single one of the terms. You can't ask for that kind of structure. The more structure you see, the easier it is to memorize, the easier it is to actually apply it and use it. So the major things you're trying to memorize is what happens to the signs. Sine is the nice one. Plus to plus, minus to minus, flips for cosine. The next main thing to remember, the second thing, is the arrangements. The sine version goes sine, cosine, cosine, sine. The cosine version goes cosine, cosine, sine, sine. But the third thing, well, that's just automatic. If the angles go alpha, beta, this is arranged so it always goes alpha, beta, no matter what. So it's a lot to memorize, but the more you see, the more you think about these patterns, your brain craves that. It's going to make mental traction happen. It'll be easier and easier to use these identities. We'll discuss the tangent one when we go to do these. And next piece of advice is the next thing that's going to help to memorize these a lot for the purpose of the exams. This is a good thing to remind ourselves. The math controls my exam policy, so they don't allow me to put a formula sheet on exam 3. I do get the opportunity to do that for the final exam, but not on the intermediate exams. Best way to be ready for these identities on exam 3 is just to write them down every single time you use them. And that's what I'll be doing on these notes, to just drive that idea home. If you do the same on the homework, then I promise you it's going to feel like second nature when you try to do them out for exams. So let's see if we can get to one problem down. It's a cosine pi over 12. So the first thing we have to do is think, how does it fit into all this? But you can take a pi over 12 and rewrite that thing. Pi over 12 is the same thing as 4 pi minus 3 pi over 12. You can divide 12 into both. This is 4 pi over 12 minus 3 pi over 12. You can simplify this. 4 pi over 12 is just pi over 3. That's going to be the angle alpha. 3 pi over 12, that's just a pi over 4. So that's going to be our angle beta. So this one's kind of weird in a way. You have to split up the angle pi over 12. We'll practice a few problems just like these in the notes. There'll be some in the homework as well. But then you just rewrite this as cosine. Here's the pattern that we're trying to hit. alpha minus beta. We're using minus because a minus appeared when we decomposed pi over 12. So this will be cosine alpha, cosine beta. The minus sign here flips to a plus sign. And the more you just write that out, even though we haven't made big progress, it's just the formula, easier it is to memorize. Sine alpha, sine beta. Then we plug in the values for alpha, beta. We have them highlighted in the right. This turns into cosine pi over 3, cosine pi over 4, plus same exact order, sine pi over 3, sine pi over 4. But chapter 5 prepared us for this kind of work, and so does section 6.3, the inverse trig functions. We know how to evaluate these ones. It was cosine pi over 12 that's the mystery here. That's 15 degrees, and this is going to be a good reason why we can finally explain 15 degrees increments was never on our unit circle diagram. We went by 30 degrees because the answers to the 15-degree increments are pretty messy. Let's simplify these down even further. Evaluate means crank it out until you get a number, and it's still not done. At this stage, we just used the addition formula. We broke down pi over 12. I should write down that intermediate step as cosine 4 pi over 12, or pi over 3, minus pi over 4. I should really be there just to connect the idea. Then I cited cosine alpha minus beta. This is just me rewriting the identity in this middle step. And here we plugged in the angles we were using. Any questions at all, folks, getting down to this line here? Okay, let's crank it out then. Cosine at pi over 3 is square root 3 over 2. Cosine pi over 4 is the same as sine pi over 4. Both of them are square root 2 over 2. Sine at pi over 3, that's equal to 1/2. Or hang on, I think I got these backwards. Let's try this again. So if you're screaming at your screen that I messed it up, you would be right. Cosine pi over 3, this is still a great diagram to write in, so you don't make silly mistakes like that one. Cosine at that angle is not root 3 or 2 at all. It's 1/2, right? So we would have gotten a 1/2 here. At pi over 4 is a root 2 over 2. Sine pi over 3, that's the value close to positive 1, root 3 over 2. Times sine pi over 4, square root 2 over 2. That looks a little bit better. It's good to get these in the right order. This simplifies further. This is just root 2 over 4 plus root 3 times root 2 is root 6 over 4. So the whole thing is square root 2 plus square root 6 over 4. And you can do that for 15 degrees, 30 degrees simplifies, 45 degrees simplifies. You can now do 60 degrees simplifies, but things like, say, 105 degrees is something kind of like this one. So these are kind of interesting values that come out. We did it, folks. We took cosine pi over 12. By the addition formulas, you can keep on working backwards. You might find out, what is cosine pi over 24? This is the stuff people did back in the really, really old times when we didn't have calculators to compute these values. They had to rely on other tricks to get these computations to come out and get the exact values like we see on this one. But we'll look into this more when we return next class on Monday. Kind of a short week, thanks to the Amazon Web Services going down on Monday. But any last questions at all, folks, on the major ideas at the moment? Okay, one of the things I'm going to be doing on the Canvas page when we return on Monday's class is I'm going to put down some extra information here, some exam 3 information a little bit early. I'm going to compile on just one sheet a list of identities that you should have ready to go, memorized for the purposes of exam 3. That way you're going to have a one-stop shop of what do I need to know, what it must be memorized. And that can let you get started on doing things like other strategies, maybe flashcards and so on. This is already effective strategy. Write down the identity every single time it comes up, and you'll dream about it. It's just going to be part of your muscle memory at a certain point. But have a great weekend, folks. We'll be back down to seeing how this one goes next class. We'll just work out the right identities here for tangent.
All of this for
Sorry, say again?
that. One view is terrifying.
Yeah, I agree with you. It's kind of this idea as well. We break down 23 pi 12s in just the right way. So things simplify down to what we know. Then we just plug it right into the big identities, one or the other. Thanks. Have a good one, Alex. Yeah, they look bad at first. I think these ones are kind of intense. The next ones aren't so bad because if you look at example 2, you're just putting this together as sine 3 phi minus phi. Turns into sine 2 phi, you just had to know the identity. So some of them are extremely fast. These ones are more kind of crank it out to get a number out. This one's just going to combine to cosine pi over 6 plus pi over 3, but that just turns into cosine pi over 2. So it's just a 0. So some of them will go pretty quick, some of them are a little bit longer.